Dear students, today we will study some few concepts like the electric field lines, electric flux, and Gauss law. So the idea of this lecture actually began before the discovery of electricity. So when humans tried to explain the shape of magnetic fields. So usually to explain the shape of a magnetic field, if this is a magnet and this is north pole and this is south pole, usually we use some imaginary lines to show the direction of the magnetic field. Today we would like to do the same with electric fields, and actually this idea came from Faraday. So Faraday suggested to use imaginary lines to describe the direction and the magnitude of the electric field. So these lines actually should be tangent to the electric field. So the direction of electric line flux should be the same as the electric field. So if this is the direction of the electric field, my lines, the direction of these lines should be the same direction as the electric field. Also, the number of lines per unit area is proportional to the magnitude of the electric field. So of the number of lines of electric field lines passing through an area is proportional to the magnitude of the electric field. And if to draw these lines, these field lines, so if we have a positive charge at the center here, if we will use a test charge, so the force between the tested charge and this positive charge is a repulsive force. So the repulsion will make the tested charge move in this direction. If I put the tested charge here, due to repulsion, the tested charge will move in this direction, and so on. And as you see, always this direction of the motion of the tested charge is outward. But if the charge in the center is a negative charge, it will make an attraction with the tested charge, and therefore the tested charge always will move to the center. So the direction of the field around a negative charge is always inward. So far they decided, yeah, we can use imaginary lines to explain the direction of the field. So to show the direction of the field around a positive charge, we'll always draw imaginary lines outward to show the direction of the electric field around a positive charge. Also, as we said before, the magnitude of electric field due to a charge is constant multiplied by the charge over the distance square. So increasing the distance will decrease the value of the electric field. And also we said that the idea of Faraday is that we can express the direction and the magnitude of the field using some imaginary lines. These lines we will call them electric flux lines. So the magnitude of the electric field is proportional to the number of these lines. So one can, from this relation, from these two relations, this relation number one and this relation number two, in relation number two, increasing the distance will decrease the value of electric field. So consequently, from relation one can also say that close to the charge, the number of field lines is large, but away from the charge, the number of field lines is smaller. So here, if I count the number of, so if you see close to the charge, the number of lines are close to each others, but far away from the charge, the lines is far away from each others. So close to any charge, the number of lines is large, but away from this charge, the number of lines is smaller. So here the idea of Faraday is just we can express the value or the magnitude of the field and the direction of the field using some imaginary lines. If we study the electric flux lines between positive and negative charges, so if I put a test charge here, the test charge will make a repulsion with a positive charge, but at the same time it will make attraction with the negative charge, so this test charge will move in this direction. If I put it here, it will move in this direction, and so on. And as you see, always the lines start from positive charge and ends at the negative charge. Also, there is no intersection, there is no cross between any lines. So always the lines starts from the positive charge and ends at the negative charge. Also, so the lines first shows the direction of the field and also can give information about the magnitude of the field. So here the lines are so dense, a lot of lines, but here the number of lines is small. If this is area 1 and this is area 2, from this figure one can conclude that the field at region 1 is more than the electric field at region 2, because the number of lines in region 1 is more than the number of lines in region 2. And just to know how to, there are some rules to draw these lines correctly. First of all, the lines always start from positive charge to the negative charge. Also, the number of lines drawn is proportional to the magnitude of the charge. So we said before that the number of lines is proportional to the magnitude of the field, but also the magnitude of the field is proportional to the charge which produces that field. So from these two laws, one can conclude that the number of the electric field is the number of the field lines is also proportional to the magnitude of the charge. Also, in all plots, if you study these plots carefully, you will conclude that there is no intersection between field lines. So no two field lines can cross each other. These three rules one has to consider when he starts to plot the electric field lines between charges. If so here to draw the field lines between two positive charges. So as we know, positive charges, the force between positive charges is repulsion force. So also, as we said, the field lines starts always from positive charge, but here there is no negative charge, so always the field lines is outward. And at region C is somewhere at the middle between the two positive charges, so the field lines cancel each other, so then there is no field lines here because the field here actually is equal to 0 at point C, so there is no lines here. And if we have positive and negative charges, as we said, the number of field lines always start from the positive charge to the negative charge. But here we assumed positive 2 and -1. So we have so the magnitude of the positive charge is twice the magnitude of the negative charges. And as we said, the number of field lines is proportional to the value of the charge. So here the positive charge is greater than the magnitude of the negative charges. So if you count the field lines around the positive charge, it will be more than the field lines around the negative charge. So actually, if you count the number of field lines around the positive charge in this figure, it will be 16 lines. But here it will be only 8 lines. So here always the number of field lines is proportional to the value of the magnitude. So the number of lines leaving a charge positive 2q is twice the number terminating on a charge minus q. Something in nature similar to the field lines. So if we have a cloud which is positively charged, and we have the earth which is negatively charged, and when the voltage is sufficient to make this charge, a current will produce from the positive charge to the negative charge. So this is what this is lightning. So always the field lines start from the positive charge to the negative charge. So Gauss tried to conclude these ideas in a law. The law, we call it Gauss law. So we said that the number of field lines is proportional to the magnitude of the electric field, and the magnitude of the electric field itself is proportional to the charges which produce that field. And so one can conclude that the number of field lines is proportional to the charge. So the number of field lines around any charge is proportional to the value of that charge. So Gauss's law states that the electric flux through a closed surface is proportional to the charge contained inside the surface. So if we have if we have a charge, this charge will make a field. These lines show the direction and the magnitude of the field. To calculate that field, one has to draw an imaginary surface, like a sphere, for example, and one should count the number of these field lines. And if we know the field lines, the number of the field lines, we can calculate the value of the electric field. So this is actually the idea of Gauss's law, and we will show an example later. But how to count the number of field lines that passes through a surface? So for example, if we have the surface, and this rows shows the field lines, actually the number of the field lines is the value of the field multiplied by the area of that surface. But the general law actually is the number of the field lines is the magnitude of the electric field multiplied by the area multiplied by cosine theta, where theta is the angle between the field and the perpendicular direction to the surface. So in this case, this line is a perpendicular to the surface, and these lines is the electric field, and one can conclude that the direction of the field is parallel to the direction which is perpendicular to that surface. So in this figure, the angle theta is equal to 0 and the cosine 0 equal to 1. So when the field lines is perpendicular to the area, one can simply say that the number of the field lines is the product of the magnitude of the electric field and that surface. To apply Gauss law for a pointed charge. So if I have a pointed charge, and as we know, this is the direction of the field lines, and the electric field due to a pointed charge is simply the electrical constant multiplied by the charge over the distance square. And we know that the number of the field lines is the electric field multiplied by the area of an imaginary surface, a closed imaginary surface around the charge. So in this case, to count the electric field in all lines, we will draw an imaginary surface. So in 3 dimensions, so in 2 dimensions, this is just a circle, but in 3 dimensions, it will be a sphere to surround the charge from all directions. So here, the area of a pointed charge multiplied by the area of a sphere, and at the end, if you also substitute with the value of the electrical constant, so if you look to the first lecture, the electrical constant actually is 1 over 4 pi epsilon 0. If we substitute with the value of the electrical constant, so at the end 4 pi will go with the 4 pi, and at the end the number of the field lines will equal to the electrical field multiplied by the area of the imaginary surface will equal to the amount of the charge inside that surface divided by epsilon 0. So here phi E will equal to E multiplied by A, which will equal Q over epsilon 0. So this law is Gauss's law. So actually Gauss's law summarizes the idea of Faraday. So Faraday said the electric field can be explained by imaginary lines, but Gauss turned this idea into a law. So now the number of field lines is equal to the electric field around the charge multiplied by the surface of an imaginary closed surface, the area of imaginary closed surface, equal to the amount of a charge enclosed in that surface over the permittivity. And actually this law can be used to solve complicated problems. So if I asked you to calculate the field around plane sheet of charge, so if we have a sheet like this, and this sheet is charged with a positive charges, and I asked you to calculate the electric field around this sheet. So the classical idea, as we said in pointed charge scenario, you can divide this surface into small elements. So each element has a charge Q, and one can calculate the electric field of each element, and at the end one can calculate the total electric field around this sheet by summing all electric fields coming from all elements. But this scenario is complicated, so the easiest way is just to use the idea of Gauss law. So Gauss law said the number of the field lines equal the electric field multiplied by the area of the imaginary surface, which equal to the charge over the permittivity. From this law, so here simply this is the sheet. If we draw a cylinder around this sheet, the field lines outward from the sheet will cross these two surfaces in the cylinder. So simply one can apply Gauss law. So the field lines goes up, will cross this surface if the area here is E null, and also the area of the other side is also E null. So in this case, the electric field multiplied by the total area. Here, observe that we have two areas, the upper area and the lower area. So A null plus A null. So here one can say E multiplied by 2A null equal to the Q inside the sheet over epsilon null. So here one can say E will equal to Q over 2A null epsilon null. And from definition, if you look to our previous lecture, we defined a new concept, sigma, which is called surface charge. So the surface charge is actually the charge over the area. So we will take Q over A null as a sigma. So so one finally can come to this results. So the electric field will be sigma over 2 epsilon null. So observe that sigma is the surface charge density, which is equal to Q over A null. So simply by few steps we calculated using Gauss's law the electric field around a sheet. So actually this quiz is just for training, but I hope that after this small lecture you can at least know these few points. First, you know the rules for drawing electric field lines. You know the definition of Gauss's law, and also you can use Gauss's law to drive the electric field around a non-conducting plane sheet of charges. And have a nice day, and yeah, enjoy the video. Thanks.